Hello, welcome back to the second half of the video lecture for Chapter 5. So we have been discussing different probabilities and random variables for discrete and continuous values. This lecture starts off with the probability distributions, and we'll be looking at a custom discrete probability distribution, how to find the expected value and variance. Then we'll look at a discrete uniform probability distribution, the binomial probability distribution, and the Poisson probability distribution. So the probability distribution for a random variable gives you the range and relatively likelihood of possible values for that random variable. If we're talking about discrete random variables, then the probability distribution is the probability mass function, and you'll see it written out as f of x. So that probability mass function then gives you the probability of each value of the random variable. And we can see that probability distribution graphically. So here we have this discrete probability distribution, and it's about whether a customer defaults on a mortgage or not. And so since it's yes or no, then that's discrete here. If it's no, the probability is 0.6%, and if it's yes, it's about 0.4%. So some more definitions. One is called the empirical probability distribution, and that's a probability that is generated from observations. So empirical means numeral. Results or observations. In this case, it's better to think of it as the observations that are recorded and not from some theoretical model. So then an empirical probability then from a custom discrete probability distribution can be found if it's discrete and the different possible values of the random variable have different values. And what you can do with this is describe different scenarios that have different probabilities. And the probabilities generated using either a subjective method, that is, it's based on someone's experience or intuition, or from the relative frequency method. So let's look at some data that's in your book, and this goes back to the summary table of number of payments made per year. So let's say someone makes 4 quarterly payments, 12 monthly payments, or 24 bi-monthly payments. So that's the number of observations, and so the probability distribution then is these frequency observations, the number here, divided by the total. So that gives me a 15% if they made it quarterly, 60% paid their monthly payments on a monthly basis, and 25% paid on a bi-monthly basis, or twice a month. And we can get those observations from our mortgage default data if we just drop our payments per year in the columns, and then our count of customer number in the summation values. To get the mean of the random variable, all you do is do the summation of x times f of x, and sometimes it's abbreviated as E, capital E of x, or mu here, and that's the formula for getting the function. We'll see on the next slide how to do that calculation. Notice this is a summation of x times the f of x function. So when we go to this screen, you can see we have x, and the f of x, or the probability mass function, then is we have our value x times that f of x is 0.6, 12 times 0.6 is 7.2, and 24 times 0.25 is 6. So our mean or expected value is 13.8 payments per year. And we can use the sum product function in Excel in order to get that expected value for us. And then for discrete probability distributions, the variance can be calculated as the value minus the mean squared times that f of x function, and we would sum that for each of the values that we have. So if the expected mean is 13.8, then we would do our subtractions. That's the x minus mu. So we have these values here, and that's what these values are here. When we'd square that times those probabilities right here, and we would get 42.36 as the variance. And so the standard deviation then is just the square root of that, and you would take a positive square. So in our case, the variation or standard deviation is 6.508. Again, if we laid out all this information in a spreadsheet, we can calculate it out again using the sum product. So we've got this value now, column C, so that's where this range C comes from, and then we're just using column B here as our percentages. So that gives us the variance. I can take the square root of that variance using the SQRT function, and that'll give me the 6.508. So let's continue on. And so with the discrete uniform probability distribution, some things that you need to consider is when all the values of the probability mass function are equal, then the probability distribution is a discrete uniform probability distribution. Think about what that says. All the probabilities of those random variables are the same. So if you flip a coin, what's the probability of one side? It's 50%. The probability of the other side, 50%. So there's two options. So the discrete uniform probability mass function is 1 over 2, or 50%, for flipping the coin. Thing is that you need to remember is that when they all have the same probability, then it's going to be a discrete uniform probability distribution. The same thing holds for rolling a die. The outcome, if it's not weighted or anything, for each side showing up is 1 over 6, because there's 6 sides. A special discrete probability distribution is called a binomial probability distribution. And this occurs when you have only 2 outcomes from your experiment. So if you look at this definition, so you have a fixed number of repeated identical and independent trials, and there are only two possible outcomes: success or failure. The probability mass function for a binomial random variable is as follows. So the mass function is equal to what you see on here, n over x, or going from x to n, where x is the number of successes. I'm sorry, x is the number of successes and n is the number of trials. P is the probability of success on one trial times 1 minus p raised to the n minus x. And x again is the number of successes. So let me go over this again. So this probability mass function for a binomial random variable, that is one that takes on a discrete value of only two options. The way you calculate that is the number of successes in n trials times the probability of x times 1 minus the probability raised to the n minus x. And we have the definition of these here. So the probability of success in n trials is calculated using this formula. So that's n factorial divided by x factorial times n minus x factorial. And you can actually use a function in Excel called fact that will calculate the factorials for you. So if you will, I'm going to switch this over for you and just show you something I actually did here. So I put in here the factorial of 3 is 6, and that is 3 times 2 times 1. So if I put in, say, 7 here, the result is 5040. So that would be 7 times 6 times 5 times 4 times 321. And it gives us the same number. So that's what factorial is. And now we can calculate the rest of this function out. Now your book already defined that a probability of success was 0.3 and the probability of failure then is 1 minus 0.3 or 0.7. So if we're using this formula here, so the probability of the number of successes, so this is on just 0 trial, and then we have n minus x, so 3 minus 0, so that's where the 3 came from here. And we can just work our way down through here, and it gives us the probabilities of what happens when we have a number of trials. So your book then goes on to ask, what happens to what is the probability that no more than one customer clicks on a link? And so we're just using the cumulative probabilities here. We would just add up, well, for 1 it's 0.441, but there's also 343, so we add those up, and that totals to 0.784. So there is a 78.4% chance that out of 3 trials, only one person will click on the link. And here we see a graphical representation of that probability distributions for the number of customers who click on a link using Martin's targeted email. So hopefully you're following along in the book and you're seeing exactly what this is. So for 0, that probability is 0.343. This is 0.441. This is 0.189. This is 0.27, I believe. Yeah. Now, since we know this is a binomial distribution, that is, there's only 2 outcomes for each trial, we can actually use a function inside of Excel called binom.distribution, as long as we know the number of trials and the probability of success. The first parameter you see here in this first function is A5. So that is the number of trial. Which trial is it? The second argument is the number of trials. Notice that this is all absolute addressed, so that we can copy it down and it won't change. The third item or argument here is the probability of success. And then we have the option of choosing either false or true. If you choose false, it just gives you the probability for that particular trial. If you choose true for this last argument, it gives you the cumulative probabilities. So here is, what's the probability that 1 out of 3 will do it? It's this amount. 2 out of 3 will select, or 3 out of 3 this. Now, if we're looking at, okay, what's the probability that only 1 will do it? You add up these two values, and that's where the 784 gets to. If 2 out of 3, what's the probability that 2 out of 3 will do it? Then it's this cumulative here. That is, 2 or fewer will click on the email link. Another type of discrete probability distribution that you'll be exposed to is a Poisson probability distribution. And that's usually useful when you have your random variable and you want to estimate the number of occurrences that an event will occur over a specified time period and space. So examples might be the number of patients who arrive at a health clinic in an hour, the number of computer server failures in a month, so there's the time component, number of repairs needed in a 10 miles of highway, that's space, number of leaks in 100 miles of pipeline, again space. I believe that should say or space, not and space. In order to use the Poisson probability distribution, you have to satisfy two of these properties. One is the probability of an occurrence is the same for any two intervals of either time or space. So the probability of having 4 things in a highway to fix over 100 miles is the same depending on any 100 miles. The second property is the occurrence or non-occurrence in any interval, either time or space, is independent of the occurrence or non-occurrence in any other interval. So we can't say that if it happens in this interval, then it'll also happen in another interval. They are independent. So the Poisson probability mass function then is calculated as follows, where mu is the expected value or mean number of occurrences in an interval. E is 2.71828, and X is the discrete random variable that shows the number of current occurrences in the interval. To use the natural logarithm E in Excel, you would just use the function exp. But there's something easier for you to use, and that is the Poisson probability distribution function. And so we can actually use Poisson.dist. And the second one is the mean of the Poisson distribution. And the third is false or true. We use false for the third argument or input, and that'll give us the probability for that number of arrivals in our example. If we choose true, that gives us the cumulative probability if that's what we're wanting. That's what you see here on your output. So if you're following along in your book, so what you've got is the number of arrivals in column A, and so what's the probability that, let's say, look at row 7. So in row 7, the probability that you'll have 3 arrivals is about 0.76%. And if we ask 3 or less, then that is about 3.03%. And so I'm going to pause it here, and when we come back, we will talk about continuous probability distributions.